Every form of life that we know of requires carbon. It's the chemically most versatile element. It's essential to all life, both as an energy source and a building stock. Without carbon, our planet would be dead. No living beings, no plants. A sad landscape of stone and metal. Yet this element builds and nourishes life on our planet. As part of food, fuels and plastics and millions of bioactive compounds, it's one of the most talented among the chemical elements. A carbon atom has 6 protons and 6 neutrons in its nucleus and 4 electrons in its outer atomic shell. It can simultaneously enter into up to 4 single bonds with other atoms. Carbon can also form double or even triple bonds with other carbon atoms and certain other elements. These properties allow for a vast variety of organic molecules, tens of millions of which are known today. Moreover, carbon forms meshes, chains, and rings like no other element. So, carbon compounds could not be more diverse with respect to structure, appearance, and properties. But even in its pure form, carbon displays an astounding diversity of structure and properties, from extremely hard, as in diamonds, to very soft, as in graphite. Each carbon atom in a diamond is connected through covalent bonds to 4 other carbon atoms. That's how you get a regular tetrahedron of 5 carbon atoms. The tetrahedra are interlinked, resulting in a highly stable structure with outstanding rigidity. Since all outer electrons are involved in bonding, no freely movable electron remains. That's why diamonds can't conduct electricity and act as an isolator. In the case of graphite, only 3 of the 4 possible bonds per atom are formed, resulting in honeycomb-like 6-membered cycles. 1 free electron per carbon atom remains, which can move freely along each layer. The 4th outer electron is responsible for both the high electrical conductivity as well as the black color of graphite. The forces acting between the layers are relatively weak, so that graphite is very soft and can be used as a lubricant. If you break down this 3D layer model to only one level, you end up with graphene. It's an aromatic system that consists of a 2-dimensional string of benzene rings. Due to this unusual property, it has 100 times the tensile strength of steel. Graphene plays a vital role in current research. Konstantin Novoselov and Andrei Geim received the 2010 Nobel Prize in Physics for their work in this field. In 1985, the chemists Robert Karl Jr., Harold Kroto, and Richard Smalley discovered the first fullerene, a further class of allotropes of carbon, for which they received the 1996 Nobel Prize in Chemistry. The symmetric C60 molecule was named after the American architect Richard Buckminster Fuller, and it's still widely known as the buckyball. Its carbon atoms are connected in 5- and 6-membered cycles, so it looks like a football.
And so we reached the stage on a Friday afternoon where Harry was going back, I believe, on Monday, and we had to wrap things up. And we said, all right, we have a paper out of finding these chains, but we really ought to think about why this 60 peak fluctuates so much. And I remember very clearly that we were sitting in Rick's office, and as a group of 5 of us, we agreed this ought to be done, and then the 3 professors looked at the 2 graduate students and said, why don't you work this weekend and see how intense you can make this carbon 60 peak? You can't ignore a result like this. It was a result sort of like this one that made us believe that we needed to investigate this further. What we knew about the chemical conditions implied that carbon 60, and to a lesser extent carbon 70, was a survivor of chemical attack by carbon atoms. And so one wanted, therefore, to come up with some unique structure for the 60 carbon atom peak that would reflect this chemical inertness. We've already seen the chains. The chains typically have a dangling bond at each end. And so this would be a site for chemical reaction, just like the divalent carbon here would be a site for chemical reaction.
Fullerenes are found in the debris of meteorites and in space. And even now, the potential of this breakthrough discovery has not been fully explored. In relative terms, there's actually very little carbon on our planet. But in the so-called carbon cycle, many carbon-containing compounds are converted and replaced in the geosphere. The German-born British physician and biochemist Hans Adolf Krebs discovered in 1937 how the different metabolic reactions within a living cell are linked to each other in a cyclic process. Here, carbohydrates, fats and proteins are degraded to yield water and carbon dioxide. In the course of this so-called citric acid or Krebs cycle, energy is generated and carbon building blocks are obtained. The cycle, therefore, can be regarded as the hub of metabolism. For his discovery, Krebs was awarded the Nobel Prize in Physiology or Medicine together with Fritz Albert Lippmann in 1953. But carbon dioxide isn't only generated biochemically. Much of it is released into the atmosphere by the combustion of oil, gas or wood. Fortunately, there are autotrophic plants, which convert this atmospheric carbon dioxide back into biomass and help to alleviate the greenhouse effect. The American chemist Melvin Calvin discovered that carbon dioxide is converted into biomass and carbohydrates such as glucose in the dark reaction of photosynthesis, an achievement that earned him the Nobel Prize in Chemistry in 1961. So the carbon cycle is closed when autotrophic plants are consumed by other organisms, which in turn burn their biomass, yielding CO2. Thus the processes Krebs and Calvin identified are essential to the global carbon cycle. More than 10 million carbon compounds have been identified so far. Apart from hydrogen, no other element can be found in so many compounds. No wonder that carbon is a source of fascination. Metals or metal complexes are often used as catalysts, increasing reaction rate and yield. Some of them are very important for industrial processes. One of these is the Ziegler-Natta process, which is used to make polymers such as polyethylene.
Eigentlich hatten wir dieses Problem, zu einem echten Kunststoff vorzustoßen, schon aufgegeben. Aber wieder hat dann der bekannte Zufall weitergeholfen. Und der bestand darin, dass uns eines Tages, und zwar in einem Versuch, bei dem wir aus dem Aluminiumpropyl ungeradzahlige Ketten aufbauen wollten, dass uns in diesen Versuch, ohne dass wir das zunächst erkannt hätten, eine winzige Spur metallischen Nickels hineingeriet. Nachdem wir das festgestellt und den Grund auch aufgefunden hatten, das dauerte etwa ein Vierteljahr, bis wir dahinter kamen, woran es eigentlich gelegen hatte. Wir fanden nämlich statt vieler weiterer nickelanaloger Stoffe völlig neue, hochaktive Polymerisationskatalysatoren, mit deren Hilfe man schon bei Atmosphärendruck ein ganz hochwertiges Polyethylen herstellen kann.
Today, this method is used to synthesize more than 100 million tons of polymers per year. In 1963, Karl Ziegler and Ziegler-Natta were awarded the Nobel Prize in Chemistry. But they weren't the first who came up with the idea. In 1912, Victor Grignard already showed how magnesium can catalyze carbon-carbon bond formations. For the development of his Grignard reagents, the Frenchman received 1/2 of the first Nobel Prize awarded for organometallic chemistry. Thanks to his work, the interest in this field increased considerably. A major advantage of organometallic chemistry is its capability to make reactions more efficient, requiring less energy and causing less toxic waste. This potential is still not exhausted.
Today, some of the most capable synthetic organic chemists claim that they can make anything. But what is increasingly important is how to synthesize them. And if you think about that, in your head, that's all you need. Any organic compound. We must do it in a green way, and here's my definition of a green chemistry. First of all, we should make any organic compound Any is a very important term. Any synthesizable, maybe. In high yields, Y. In high efficiency, E. In high selectivity, without producing any other isomers and so on, preferably, S. In YES, in a yes manner, as someone in America said and succeeded with this YES work.
For more than 250 years, scientists have been on the trail of carbon. Many carbon-related discoveries and inventions have improved our quality of life. Today, humankind faces the issues of climate change and a looming energy crisis. Carbon-based compounds appear to be part of both the problem and the solution. Their diversity offers us unique opportunities to overcome these challenges. It's up to us to do so.